be done, you know. I guess you guys will be excited to hear that. Or more. Okay. Okay, any question, anything?
No, it's just
Everything is
baseboard.
going well
There's no
with the
more.
project? Problem is solved, you know, nobody got the answer, you know, we change the voltage, everything is good now? Okay. Now, we talked about the resonance converter, we talked about the resonant inverter, how it does work, we discussed it, you know, if you're leading or lagging, and the effect of, you know, switching loss. Basically, the main reason you're using the resonant converter, you have lots of things. Why? Because they are load dependent. When the load Q, the load keep in mind Q, you know, we assume high Q, right? High Q because we assume the rest of the harmonics is zero. They are not. But you know, this is load dependent. If you have a low Q, so the current waveform is going to be a little bit different. The zero cross is going to be a little different. But in general, is based on the application, you select this one. You know, what is the main advantage of resonant converter? We switch either at zero voltage or zero current to reduce the power loss. So when the circuit we discussed, you know, if we are not exactly at the resonant frequency, what is going to happen? We are going to one side. We are going to have a soft switch. On the other side, when we, for example, we are turning off the switch or we are turning on the switch, we are going to have some losses, right? So basically, we save half of the switching loss. Now, the one we discussed it was an inverter, and we are going to talk about more about the DC to DC converters. They are very popular for DC to DC converters. Series resonant I'm gonna go with a half bridge on the primary side, but easily you can make it full bridge and you can discuss it. You know, the half bridge and full bridge, how it does work. There's a little bit more discussion on how the circuit works and everything else, but they're very similar. The half bridge and the full bridge. I call this one C1C. And this is it. V in is the V in over 2. So basically, we assume C1 and C2, they are very, very big capacitors. Very, very big capacitor. The result is VC1 is equal to VC2 and equal to V in over 2. This voltage is kind of tight. Fixed voltage is not, in reality, that's one of the problems. These two voltages, they are not exactly the same. But here we don't consider that part. We assume that voltage is divided perfectly between these two capacitors. Now on the this one is not isolated. This is not isolated, but later on I put the isolated one also there. This one is going to another diode rectifier now. Because look at it, this is like the inverter, right? This is like the inverter. You know, you have V in here. What we are going to see here is going to be V in over 2 and minus V in over 2, right? So basically here we are going to see another AC voltage. If it's going to be DC to DC, this is a DC, right? We converted this DC to AC, right? I need another rectifier to make it DC, right? So we'll put the diode rectifier here. We call this one DR1, DR3, DR2, and DR4. Let's call this one VCR, and this is the LR, CR, and this is the ILR. And this is the positive direction. If the current is going this way, we consider current positive, right? If you're going other way, if you say current is negative, means it's going that way, right? So here we have a capacitor and inductor, which is going to filter the current. This one is called C0 and R. COR is the VO, and let's say this is the filter version of IO. Let's call it. And this one is the, how should I write it down here? IO. Is it correct? What does it mean here? This is a rectifier, right? If we have a sine wave from current here, right? This one is going to rectify. I put the absolute value of ILR, right? If the current here, the current is like this, right? Sorry, no. Like this, right? This is the inverter, right? This current is the AC current. We discussed this one last class, right? So what current we are going to see here? Rectified version of this one, right? So that's what I mean this when I put the absolute value of IR means, you know, just rectified version of ILR, and I0 is kind of filter version of this. What's the relation between I0 and ILR? Can you tell me? If ILR, let me put it this way. Just I wanna remind you this one. If this is the ILR, let's say perfectly sine waveform, right? If this is the ILR, and let's say this is the IM, and this is the IM. I'm not sure I use the M or something like this. IM. Let's call it IM for now. So this current is which one? That's the ILR, right?
Mm-hmm.
How much is the IO? Somebody tell me.
Give me the average of that.
This capacitor ideally is going to filter out all the AC component, right? The only one can go over there
DC.
is the DC component. How much is the DC component of this one? Ideally, IO is going to be like it. Right? That's from the power electronics one, right? Full wave rectifier, how much is the output voltage? 2 VM over pi, right? Or 2 IM over pi. You guys can remember that, right? It was last quarter, not that long ago, right? So it's a 2 IM over pi, right? Ideally, I'm saying ideally is a kind of a flat current like this. Just keep this one in mind because we're going to use this one. Now let's think about this circuit, how it is going to work. This circuit. Again, let's call this one S1, V1, S2, V2, right? There are different cases. If the current is going this way, right? If the current is going this way, either can come through here, right? Or either can come through here, right? So there are two cases when the ILR is positive. There are two cases when ILR is negative, right? When it's negative, can go through this diode, right? Or can go through this switch, right? Four cases. Let's put the circuits quickly together here. So if ILR is positive, I mean the current is going this way, right? If ILR is positive, so two cases. One, S1 is on, right? Could be one case, right? If S1 is on, how much is the VAB? Somebody tell me. How much is the VAB?
Half of V.
If this one is on, if this one is on, this point is connected to V, right? How much is this one? V, right? Over 2. So how much is the difference? V over 2, right? So it's going to have a V. V over 2. How about VCD? So now look at it. We are in this part. We are on this part, right? Of the ILR. We said ILR is positive. Which one of these two? Which one of these four they are on? DR1 and DR2 will DR1 and DR2 they will be on, right? So basically, if we are here and this one is positive, DR1 and DR2 also they are on. So how much is the VCD? If this one is on and this one is on, this is a VCM, this is a VD, right? C is connected to positive side, D is connected to negative side of VO, right? And we assume the output voltage is a DC to DC converter. This capacitor is very big and this voltage is fixed, right? So VCD is VO, right? That's one case. The second case is still for ILR positive. If ILR is positive too, it's still ILR positive, but now, which one is on? D2 is on, right? If D2 is on, how much is the VAB? Minus V over 2, right? If this one is on, right? VA is connected to how much? 0. VB is connected to V in over 2, right? VA minus VB is a minus V in over 2, right? So this one is minus V in over 2. How about the current? That still is going this way. Which one is on? It's still DR1 and DR because the current is positive still, right? If the current is going this way, this one and this today have to be on, right? So again, DR1 and DR2 they are on. So VCD is V1. So if the current is positive, there are two cases. Either this switch is on, either this one is on. And we see the equation here, what it is. Now, if the current is negative, right? If IL1, if the current is negative, means the current is going this way, right? The current is going this way. Either S2 is on or V1. Let's write both of them. One case would be S2 is on. If S2 is on, how much is the VAB? If S2 is on, means A is connected to 0, right? So this one is a minus V over 2. So if the current is going this way, which one of the diodes here is on? 3 and 4, right? You guys, it's clear, right? Then I'm saying the current is positive going this way, so this one and this one they are on. If the current is going this way, these two they are going to be on, right? D3, DR3, and DR4 they are on. How much is the VCD? If this one is on, look at here, D is connected to positive, right? If this one is on, C is connected to negative. So VCD is minus VO. Another case would be maybe D1 is on, right? If the current is negative, maybe D1 is on. If D1 is on, how much is the VAB?
Positive
V in over 2. If this one is on, A is connected to V in here, right? So VAB is V in over 2, and this part is the same thing. VR3 and VR4, they are on, so VCD is minus V. Yeah, I forgot to plot the circuits for each case. Case 1, we have a circuit like this. We are going to have a I'm not sure what we call it, VC. Yeah. Right, circuit is going to be like this. Case 2, which D2 is on, is going to be like this. This one is going to be BA, right? Because VAB is negative, right? So still the current is going this way, right? ILR is positive, right? Still the current is going this way, and this is a C, D, and this is a V. Oh, sorry, this is called right? Case 3, case 3 and 4. If you look at VAB is negative minus V in over 2, so basically again is like this. But the voltage is negative, so basically if C is here, D is here, it's going to be like, let's put it this way, D, C, D, O, and this is the V, right? The current is going this way, right? And for the last case also is like this. Again, here is LR, CR, current going this way, and this is the D and C. Four different circuits, but they are basically all the same. Simply we can summarize all of them in one circuit and put it like this, for example. All these four can be summarized in this one. So we have a plus minus V in. A source is changing like this. A, B, LR, CR, ILR. And here again, it's going to be plus minus, this is a CD, but this one is going to be plus minus V, right? And I have one of, each of them is going to represent one of these. Now let's draw the wave, see how they're going to be. We'll start with the VAB. Let me put it here. We are working with a 50% duty cycle, right? This is a V in over 2 minus minus V in over 2, okay, up to here. And now, let's plot the VC number. Let's say VCD, there is a shift, right? This is a VO minus V, right? That's a VC. And now let's go with the current. ILR. It's going to be like this. So basically, if you are going to go with this number, which case is this one? Here. Tell me the case. Which case is this one? Look at here. VAD is positive, right? And ILR is negative. VAD positive and ILR negative. So this is a case 4, right? VAD positive and ILR is positive. Case 1. VAD negative, ILR is still positive. 2, yeah. And definitely this one is case 3. And you're going to repeat here. 4 and right. These are the 4 cases we have. If we do the set. Now, I want to plot the IS1 here. How much is the IS1 during this time? Let's start from there. Case 1. Case 1 switch is on, right? IS1 and IS1 and ILR, they are the same, right? So basically it's like this. Case 2, how much is IS1? 0. Again, it's going to be 0 until when? Right? This is going to be a new thing. Right? Oh, I don't have a space to put the VS1. You guys, you can put another one under this one, then I'm going to plug the VS1. How much is the VS1? Yeah. How much is the VS1? Yeah. This is killer, right? I don't know. Like, can you see the difference between the colors? I'm not sure. And this is a VS1. Oh, sorry, I put the wire there. When the switch is on, VS1 is 0. When the, again, when the switch 1 is on, the voltage here is 0. And again, either this one or this one, either of them, they are on, this voltage is 0. When D1 is on? Which case was the yeah, case 2. Basically, the voltage is going to stay 0. Am I right?
Case 4.
Case 4? D1, you're right. I'm wrong. Case 4, here. right? It's gonna be right. Here, the 1 is on. Here, S1 is on. So, from here to here, none of them they are on. Again, here is everything is on, right? From case 2 and case 3, one of these ones they are on, right? One of this one they are on. How much is the voltage here? See, this is one of this one is on. This is short, right? This switch, one side is connected here, and the other side is connected here, right? How much is the VS? V, right? So basically, it's going to be like this. Very similar to the inverter discussion we had. This is a VSC, right? What is happening here? This is a ZCS plus ZVS, right? So first of all, you can see the voltage across the switch is 0. If you switch, there is no loss. Or you can say even better, my current also is 0. This is 34. But here, no. My voltage is something, is a V in, right? And the current is not 0. Here I have some switching loss, right? Very similar to the inverter we had before. And this is a V in. Now, instead of having something like this, I want to get a better, general, equivalent circuit for the loop. Now let's look at this. Let's look at it. I said, look at here. I didn't put the resistor here for any of them, right? There is no resistor here, right? I want to put a fake resistor instead of this one. I have an R here. Just I want to know if I want to draw it here. We call it AC resistor or effective resistor, right? Let's think about how we can do that. Can you help me how we can do that? Calculate that one. It could be power, Either in this circuit or that circuit, we should have the same power, right? And let's consider only the fundamental harmonics, right? I should have solved one example. There's in the book. Maybe I'll go over. You can see I think the design is 60 watt or 65 watt inverter, and the third harmonics is 0.6 watt. So basically, all the power is transferred by the first harmonics. We discussed this one when we started the inverters, right? You remember the single phase inverter when we started this course at the beginning of the quarter? We went through that one to show how much of power is transferred by the main harmonics, and the rest they are doing how much. So basically, almost you can assume, hey, there is no other harmonics. I'm going to go with the first one. So I have only one harmonics, which is the first one, and I go based on that one. I'll find the effective resistor to replace it here. Let's see how we can calculate that. So VAB 1, fundamental. How much is it? What's the fundamental of this one? We said if you have a square wave, it's going to 4 VDC over pi, right? For the first one. So it's going to 4 times how much? V in over 2 over pi. Basically, the 2 V over pi, right? For the first harmonics of the VAB, right? We have a 2 V over pi. How about the VCD first harmonic? How about that? How much is it? 4 V over pi, right? They have different phases, but the amplitude is the same for both of them, right? How much is I? I here, I0. How much is the I0? If we didn't have a capacitor, I0 is average of, no, let's say no. No, we know how much is the I0. I want to, give another name here, this current. I don't know what to give a name here. Yeah, we call it ID. This one is the ID. ID. Now, yes. So ID is this much, right? Is the rectified version of ILR. Now, we can say ILR if we have a high Q, right? If Q is high. If its Q is high, what does it mean? What does it mean? Hmm? Right? Is it correct or not? Is it if Q is high? Remember what we discussed toward the end of the last class? You say if Q is high, the rest of harmonics are going to be very small, right? We discussed this one, right? Look, today is Tuesday. Yeah, it was a long weekend, but it's 4 days ago, you know, not that much long ago, you know. We went through. I give you an example. You know, you put 3. I don't know. I went through the example for N3 and you see how much is it, how small it was, you know. But by the way, you can go look at your note. If Q is high, it means the current waveform is almost sine wave, right? So the reason I'm saying is this one, what I explained here. Because if the current waveform is not. So basically, ILR is like, let's put it this way, ILR 1 sine of omega t or something like this, plus something, plus a phase. I don't care about the phase, how much is the phase? Right? This is the magnitude of this current here. I call it here IM, the peak of it. Now, so we know the current ILR is a sine waveform. ID is the rectified version of this one. So ID is going to be, or IO is going to be, IO is the filter version of the ID. IO average, let's put it this way. This one means, or like this. IO average and ID average are going to be the same, right? Because the harmonics is not counted, right? The ripples is not counted. Both of them, they have the same average value, and how much is it? How much is it? Right? 2 IM here, right? So we have this one. Now, how much is the average of IO? IO. How much is the average IO? IO is fixed, right?
The
How much is the average of IO?
2 over pi something.
IO. V over R, right? V over R, right? So basically, IO average and IO, they are the same, and they are VO over R. Right, there's one equation here, I'm going to write it here. So, keep this one here for now. Now, I want to put a resistor, equivalent resistor here. This resistor is going to dissipate same power. See what I'm doing? Let's go back to the circuit. What I'm doing. I want to get rid of this part. Just put a resistor here. I call it RE or R effective. This resistor should have the same power. Let's assume everybody here is like this, right? There is no power loss here, right? This resistor should have the same power dissipation as this one, right? So how much is this one? This is the VCD, right? VCD. If this one, because I'm going to put it this way, see here? right? This is a VCD. If this current has a only first harmonic, right? How much is the power dissipation? Yeah. So see, basically this resistor times this RMS value of this current to the power of 2, or you can say this one has only first harmonics. So if I want to find this one, is the Ohm's law. It's going to be the first harmonic of this one, this voltage, right? Divided by first harmonic of this current, right? It's going to be this one, right? Now let's write it down. We said the effective resistor RE over ILR1. Both of them they are maximum. Both of them they are maximum, right? We can say R is equal to V RMS over I RMS, or you can say V maximum over I maximum, right? But again, think about it. Why I'm writing it that way? Because only first harmonic is dissipating power, right? If we had the other harmonics, no, I cannot go with one. I have to put one for the third harmonics, one for the first harmonic. It's going to be kind of very complicated. But because the power is transferred only by the first harmonics, I'm going to go with this equation. R effective is VCD1 over ILR1. How much is a VCD1? Here. Let's put it here. 4 VO over pi. How much is this one? Let's put it here. No, I want to go with here. Right now I'm going to go first with IO. So it's going to be PIO. Let's put it this way. Pi IO. Right? This is the ILR1. Right? Let's put it here. Now, let's see, is it 8 VO over pi square IO. How much is the VO over IO? Right? So R effective is going to be 8 over pi square. So when we have a circuit like this, just to summarize, when we have a circuit like this, just put it out. Put a resistor equal to 8 over pi square times this resistor. So you can replace it with that. Right? Now we're going to go calculate the gain and the rest of the thing. I'm going to review that Infineon paper, next week. We'll see, they use exactly the same methodology to model their circuit, So now if I'm going to redraw the circuit, instead of having 4 different circuits, I'm going to go with this. I'm going to say this one is going to resolve like this. I have a source here. It's plus minus B in. This is my circuit. This is my AC circuit. And this is the VO, right? This one was plus minus VO, right? Now, I'm going to use this circuit for the frequency analysis. Let's do RE or do the R. Yes, R. Now let's do the frequency analysis. In a DC to DC converter, what is the goal? Somebody tell me, what is the goal when we have a DC to DC converter? What is the goal? I want to control the output voltage, right? I have, I don't know, whatever voltage, 10 volt, 12 volt, whatever I have here. Here I want to have control the voltage. Let's see how we can do that. You know, we have a fixed input, or it could be variable, but let's say we have a fixed input, and let's say how we can control the output voltage. You want to have half a V in, half. You want to have a 1/4 of V in, half. Let's go through that. And I forgot, they call it series resonant, because these two, they are in series, right? This capacitor, and the next one is the parallel resonant converter. This one is here, the capacitor is here. And the next one is a hybrid. It's a series parallel, you know. They have different, each of them, they have application for itself, you know, what is the application. But series is because these two, they are in series. Now, I want to find the transfer function of this one. I have an AC in, I want to get the AC out, right? Let's put it for the fundamental harmonics. Let's put this one for the fundamental harmonics, right? If I go with the first one, low, let's put it this way. V81, right? How should I show this here? And VC1. How should I find this one? VC1. Right? This is a sinusoidal voltage, right? I want to see how much is this voltage. I want to see how much is this voltage. But let's calculate the first harmonic of this one. How much is it? How should I calculate this one? This is the input, this is the output. This is the voltage divider, right? I have one impedance here, one impedance here. Basically, it's going to be this one divided by this one plus this one, right? Times the input voltage, right? So let's do that one. You're going to get to this result. So VCD1 over VAB1 is equal to. I'm going to go with the just amplitude. I don't care what the phase. It's going to be this one, right? This is the RE, right? RE over how much? RE square plus, right? Omega LR. Is it plus or minus? Minus, right? Omega LC. Am I right? No, not LC. Omega C. Sorry. Omega C to the power of 2, right? Yeah, no, that's right. That's right. This is the C. Right. Just be divided by RE. If we divide the numerator and denominator by RE, it's going to be 1 over this is 1 plus omega LR minus 1 over omega CR over RE, or I should put it this way. Right? Now, let's write another one. VCD1 over VAB1. How much was VCD1? Right? How much was the VAB1? So I'm going to use this equation, 1 and 2. I'm going to find the VO over V in is going to be right? We can go with the keyword for you. We have this one now, right? Let me see. I can make the Q is better. Let me see. Yeah. I don't know how it's going to go Q. This one is equal to omega and omega 0. Okay. Now, let me plot this one. Right. How much is maximum of the VO over V in? How much is, if this one is very maximum, this one should be minimum, right? How much is the minimum of this? 1. Because it's 1 plus something to the power of 2, right? And the minimum is going to happen at what frequency? Resonant frequency, right? Let's say, let's call it omega 0. This is the resonant frequency, right? If you are at omega 0, this one and this one, they're going to cancel each other. So, how much is the maximum? Half. Now, based on what kind of Q you have, Q, the definition of Q was, Q is omega 0 LR over R. Or, I forgot this one, omega 0 was, we should write it based on C also, you know, I forgot it was the based on C. Okay, so here, let me see, if I times this one by omega 0 and divide it by omega 0, time by omega 0 is going to be omega over omega 0 times by omega 0 divided by omega 0. Time by omega 0, that's Q, right, minus. I cannot remember if there was omega 0 over omega 1 over Q or something like that. We had this one from the other, let me see here. Yeah, I think it's going to end up like this. I think it's going to end up like this. This one, this numerator is going to be 1 plus I think it's this. Let me make sure. Omega 1, yes, that's the one for the first harmonics. Now, think about it. This is the omega axis. If the omega get bigger, so this term is going to get bigger, right? Or if the omega gets smaller, this term is going to get smaller, right? So basically, this one is going to be like right? So the different thing is what kind of Q you have. See, this one is timed by Q squared, right? If you have a small Q, it's the slowing down, right? But if you have a big Q, what is going to happen? If you have a very big Q, as soon as you move from the resonance frequency, it drops, right? So for example, we can put some numbers here to say, for example, this is a Q1, for example. This is a, for example, Q2, and for example, this is a Q3, right? Now let's look at see how we are going to control. And this is a resonance frequency, right? What was the goal? We wanted to control. Let's give you the example, for example. Let's say V in is 24 volts, right? I want to control my V out to be 12 volt, for example, right? 12 volt is here. So if it's 12, you know, this is a, no, let's say not 12. Let's say we want to have VO, for example, 6 volt. Right? Because it's a 0.5, right? Here is 0.5, right? 6 volt is going to be how much? 0.25, right? So this is the line. This is a 0.25, right? I want to control my output voltage to work for whatever load I have. For whatever load, because load is variable, right? This load is going to change. I want to have 6 volt, right? I have to be on this line, right? If I have a light load, Q1 is a light load, right? It's big resistor. Light load means big resistor, right? So I have to switch at this frequency, right? Right? If my load is a little bit heavier, I'm going to go here. Over here. But this side is, I'm not sure. This side is, let me see, capacitive or inductive. Which one is it? I don't know. I think this side is capacitive. Usually we use this one. So you can see, if I want to have a point, I want to have a 6 volt for Q1, I'm going to go here. If I want to have it for load 2, here. So see here, I need to change my switching frequency in my converter, right? If I change my switching frequency, right, I can control my output voltage for any load be 6 volt, right? What is the problem with this? What is the problem? Either this way, one side is capacitive, either this way or here. One side is capacitive, one side is inductive. We use the inductive, you know. But what is the problem with this? Can you tell me? So we showed you how we can control the output voltage, right? I want to have for any load I am putting here, these different Qs. See, Q is here, right? See, Q is here, right? So if the Q is different, resonance frequency for this circuit is fixed, right? Based on L and C, right? L is fixed, right? If the Q is variable, means the load is variable, right? The resistor is variable. Now I want to have 4 different Qs. I want to have 6 volt, right?
Maybe more harmonics.
So to do that, for this Q, I have to switch at this frequency. Omega means frequency, right? 2 pi f, right? I have to switch at this frequency. If the Q is 2, I have to switch at this frequency. If Q is 3, I have to switch at this frequency. What's the problem?
It's going to be shifting the phase.
The best place I want to be is here. Why?
It's a fundamental frequency.
Doesn't matter what your Q value is.
No switching loss.
Right.
If I switch here, no switching loss, right? Why? Because we are resonating. The current is going to be exactly like this. Right? The best place I want to be is here, but I cannot be. You know, I'm saying I need to control the output voltage. I need a 6 volt, right? Based on whatever load I have, this one is going to change, right? So what's the result of these things?
Higher switching frequency.
Right? Not the high switching. The high is variable switching frequency loss, right?
Mm-hmm.
You're gonna get further and further far from the switching frequency, right? So this one is going to get more and more current. And one side is fixed. One side we are going to switch at 0. But this side is going to get worse and worse, right? With this one. So we saw how we can control the voltage. To control the voltage is very simple. It's this equation. It's this equation. Hey, you want 6 volt for this load, switch this one. You want that one, switch this one. Switch this one. This is a continuous curve, right? You can go. You will find your minimum load, your maximum load. Usually the design is like this. You go through the Infineon design. You select the minimum load you're going to have. You select the maximum load, and you figure out, okay, here, for example, is 400 kilohertz. For example, here is 100 kilohertz. Hey, let's make sure the switch I'm selecting, it can cover 100 kilohertz to 400 kilohertz, right? This switch can switch as fast as 400 kilohertz. So I'm good. I'm not worried anymore about my switch, right? So you want 6 volt, I need to move on this line based on whatever load I have. The only problem I'm going to have, I can control the voltage, but the only problem I'm going to have, the farther I'm getting from the resonance frequency, I'm going to get more and more loss. But it's still one side we are good, right? One side we are good. So this is the way you can control it. So I'm not going to give you a control loop, for the resonant going. It was good, to give you one example on this one. You guys can go simulate it in the lab to see, hey, we have a variable load, control the voltage. I want to have a 6 volt with this circuit. I want to have 6 volts here. Just go switch here. For example, put variable resistor here is a 10 ohm, 20 ohm, 30 ohm. You should change all this thing. You should see this voltage is going like this, for example, 6. When you have a load change, it's going to be like this. Again, you have another load change, it's going to be like this. You know what I'm saying? When you have a load change, you have some transient, but you get to the same voltage, right? Basically, to do this, for example, here you have to switch 100 kilohertz. Here you have to switch, for example, 200 kilohertz. You will find out this one through a control loop. You know what I'm saying? But the idea of the closed loop control is this curve. You should find the right switching frequency, right, to switch so you can get enough gain. This is the gain. Look at this one. 0.5 gain, 0.25 gain, right? You are controlling the gain of this circuit. This is a circuit. You see how much gain I want, right? And you find out. You can select that gain by the switching frequency. Yes, somebody has a question.
If your Q changes based on load, so that means your transfer function changes, right? So does your feedback circuit, do you just get an average one, or?
I don't want to get into control, but you have your Vref, right? Right, and you have your V actual, VDC, right? Whatever you are seeing there. Or controller, doesn't matter here. What's the output of this? You tell me. Error is here. This one is going to tell me the F switch. And now this one, if you look at it here, you should have a variable triangular here. This one is getting this Fs as the input, and you compare it here to this one. Basically, with this one, this is a variable. This is not fixed like the one you simulated already. You had, 20 kilohertz, 10 kilohertz, whatever you had up to this point, right? This time you change this one, right? And you get the switching function going on connected to your switch.
Won't the stability of your system change?
There are stability probably. You need to do a stability analysis for this. Is again a small signal. This discussion is really next class. Remind me, I'll bring a book. A guy, I think he's in Israel or China. He's worked for university. He has a book. I think it's maybe like 1,000 pages. He just discussed this one, just not this one. I mean, just this DC to DC converter. I'll bring it. You can go Netmo on the overall book is like 500 pages. It discusses everything. I'm saying is open. Go check IEEE. See how many papers you can find on this kind of thing. Resonant converter. Now I changed this one a little bit this way. I changed it a little bit that way. Everything is a new thing. So stability analysis, all this kind of thing. But the simple things I'm saying, you have a resonant converter, right? You want to control the output voltage, right? This is your case. Can I have, if I have a 24 volt, I want to have a 20 volt output. Can I do it with this circuit? No, this circuit, this is the maximum gain you can have is 0.5. That's it. If you want 20 volt, go find another circuit or increase your input, right? So my point is, but can I have 10 volts? Yes, you can have. 10 volts is going to be very tough to see. 10 volts is better. Why?
Switching loss.
Yeah, we are very close to the switching frequency, right? If I want a 12 volt, it's perfect. Half of the area, I'm going to be all the time here. I'm going to go with the. This is how you design. If you know your input output, you know what I'm saying? So still it could be variable load, you know. You want it a little bit this way or this way, a little bit, you know, it's not going to be this much. It's going to be, for example, like this. I'm working on a project, you know. It's not exactly zero here, but there is some current. Still the loss is pretty small. This is a design. When you optimize these things, you know, when you define exactly what you want, you can go select the best circuit. Maybe the resonant converter is not the best circuit. Maybe buck converter is the best circuit. No, because of what we talked about, you know, resonant converter, series resonant converter is the best circuit. These are the design criteria, you know, you put it there. Usually with every project when you start, unless it's a very, very clear things, you know what converter you want. But when you want to do something, you define what you want. I have this thing as an input, I want to have this one as an output. Okay, which circuit topology should I select? This is when you become expert. You know a lot about this circuit, this kind of thing. Okay, so I have a $25,000 to buy a car. Okay, if you're a car dealer, say, okay, hey, maybe you can go with Camry. I don't know. Let's put it there. Hyundai, you know, you have a range here. You know, you can go from 20,000 to 28,000. So these are. Is Tesla? Can I buy Tesla? No, you are here. Right? Tesla is gonna be here, right? So you say, okay, this is your choices. You have like these 10 choices to go select your car, right? I want a hybrid car, for example. Now you add more. Okay, yeah, hybrid, yeah, maybe you can buy Prius, you can buy, I don't know, Civic, something like that. So this is, you know, can I have a pure electric car? Yes, again, this is just Nissan Leaf. The next one, for example, I don't know, is, for example, Chevy Volt. Chevy Volt is not pure electric, it's a hybrid. But I'm saying, based on what you have as an input and what you want as an output, if there's only one option, so there's no selection, you know, I have to go with this one. But when there is, for example, 10, 12 options, now you are going to go check each one. You say, okay, now I think I'm going to go with Civic Hybrid. That's the best case based on the money, performance, all these kind of things. I'm going to go with that. Here, the same thing. You say, hey, I have this thing input, I have this much output. Now, maybe buck converter works for me because this is like buck, right? 24 volt maximum, I can get 12 volt, right? It's bucking, right? So, but let's see what's the advantage of having buck converter and having this resonant converter, right? So resonant converter is going to give me this much loss, that one is going to give me that much loss. But this one needs 2 switches, 4 diodes, buck needs 1 switch, 1 diode, right? You put all these things together, and at the end you say, no, I think the loss is very important for me. For example, I want to put this one in a hybrid electric car. Under the hood is a high temperature environment, right? So I would rather to have a less loss compared. I don't care to spend a little bit more on the parts because I have lots of loss. To cool it down is very difficult, right? So I'm going to go with a lower loss. Having less loss is important for me, so I'll go with this one. No, I'm going to put it in the corner of my room and I'm going to do this one. I don't care, you know, if I have a little bit higher loss, I want to spend less money on it, right? I'm going to go with the buck converter. So these are the design criteria. You define it and you select it, which one is the best for you. Maybe sometimes it's very difficult to find out what is the best, right? So it happens in your life a lot, you know, maybe you see one thing and you have several options and you don't know which one is the best, you know, and hopefully you make the best, the right decision to select the best, but sometimes you make the wrong decision, right? My point is, you know, this is all based on your expertise. The better you are, the better designer you are, the better design engineer you are, you can select the right circuit. But sometimes there are 2, 3 good answers, you can go with all. It's not going to hurt, you know, you can go with either. So the control idea was here. So you can control the gain from 0 to 5. Any voltage you want between 0 to 12 volts, 0 would be basically difficult because it should be asymptotic, right? But let's say, for example, you define from 0.1 gain, 0.1 is going to be 2.4. I can cover you from 2.4 to 12 volt, right? I can change the gain. The only problem we're gonna have, we're not gonna switch at resonant frequency. We're gonna get some losses. But the control loop is gonna be as simple as this one, and you can go into detail to make it as complicated as you want, right? Now let's look at another circuit. The next circuit is gonna be let's skip this one. Let me go through the example of the book. You know, we don't have the time to cover that example. I was reading this one. I like it. You know, I was reading this example. I'm going to go through the example 9.3 of the book. It's a resonant inverter. What we talked about last week. Any question? Was it clear? We're going to have one question in the final exam on the resonant converter. One question from this one question from the inverter, one question about the DC to DC converter, 3 or 4 questions, you know. And definitely one is going to be on the state space, you know, small signal modeling, something like that, you know, like the homework I gave you, very, very similar to the homework I gave you. Oh, and one on the design of the DC to DC converter, the phase margin, gain margin, those kind of things we talk, you know, select the component. Yeah, one question like that. It's going to be most probably 4 questions. 4 questions. To be honest, you know, with you guys, myself personally, I haven't worked that much with the resonant converter. I have started to work on it, you know, to build it, you know. Reading and teaching is not difficult. Well, this is a simple circuit. This is the H bridge, you know, this switch is on, that switch. But you know, when the experience comes in, you see all the problems. And then, you know, okay, how many circuits you blow up, you know, that one is going to add up to your knowledge, you know, what it is. Right now, we are working on 2, 3, you know, different circuits, you know, for resonant converters. Hopefully, I'll get more experience next year. I'm teaching this one. More experience on the real side. It says, this example, it said a 10 ohm resistive load requires, we have a load in the 10 ohm. It says it requires 1,000 hertz, 50 volt RMS, sinusoidal voltage, you know. So we have a load, is a 50 ohm. It's okay even if the frequency goes to 1,000 hertz. Can you connect your refrigerator to 1,000 hertz or not? Your refrigerator or your dishwasher, they're a little bit different because they're variable speed. But the refrigerator, if you connect it to the 1,000 hertz, what's going to happen? Just to let you know, very simple, the refrigerators usually they are induction machine. Those when they had the energy conversion, they know induction machine rotate at the very close to the synchronous speed. Synchronous speed was 120 F. I think it was overcome. It was like this. So when you have a 60 hertz 2 pole, for example, 2 pole machine, 2 pole and 2 magnetic poles. So 50 hertz times 126,000 divided by 2 is going to rotate at almost 3,000 RPM. The engine, if you look at the refrigerator, there is a motor, right? Inside that one is, for example, running at 3,000 RPM. Now if you connect to this kind of voltage, so that one is frequency sensitive, you cannot. Think about it, instead of 50 hertz with 100,000 hertz. So how much is that? 20 times, right? Or 200, 20 times, right? 20 times. So it's going to be 60,000 RPM is going to break, right? Because the motor is not designed to rotate that fast, you know. So my point is, some of the load, for example, if it's a simple resistor, maybe it doesn't care what frequency it is, right? So you can put a 50 hertz, you can put a 100 hertz, you can put a 200 hertz, whatever you want. I'm saying based on what kind of load. This is the nature of your load. You said we have a load 10 ohm, 100,000 hertz. It could go to 1,000 hertz. 50 volt RMS. You want to have 50 volt RMS across this load, right? Now you said, this is important. The THD of the load voltage must be not more than 5%. You want the voltage THD to be less than 5%, right? uh, and adjustable DC source is available. So we have a DC source, we can change the value, how much it is. Design an inverter for this application. So basically, if you go back from the last week class, this one was the resonant converter. Right? Right. So this output voltage is going to be AC output voltage, right? We have a current here. This voltage again is if you look at this AV, this VAV is like this. Whatever we put here. Right. Now we want to have this one. So let's design an inductor and capacitor, right? They're going to resonate at 1000 hertz, right? If we have that one, these two, they're going to cancel each other. Whatever voltage we have here, they're going to see here, and they're going to be the same phase, right? That's a very simple, design. But let's see how we can. The THT, we should bring it in. Remember, we said the high Q is going to do what? High Q.
Gonna make it sine waves.
More sine wave, more close to the one. So basically, if you are going to have 5%, this guy is talking about the Q, right? We should find the right Q value to give us this 5%, right? Let's go over it, see how we're going to do it. So, if we are going to have a 50 volt here, right? Let's say 50 volt RMS. We say 4 VDC over pi is going to be V1, right? V1 maximum, right? I want to have a 50 volt, so basically 50 volt times the square root of 2, this is RMS, right? I want to have the maximum. It's going to be 4 VDC over pi. So VDC is going to be 55.5. So I should go set my V in or VDC 55.5, right? And now if I have this one as switch at that 1000 hertz switching frequency, right? I'm gonna have 55 minus 55 with that frequency. If I select this component to resonate at this frequency, so these two, they are not here, right? And my current is going to be perfect sine waveform. The voltage is going to be perfect sine waveform if I have a high Q, right? Now let's go further. So we select the DC. The circuit is going to be this. Now we need to select these two values. We need to select these two values based on 5%. 5%. Now, we define a THT. THT was for the voltage in this case. Right? You add up all the harmonics, the square root of that, divided by V1, right? Let's assume we are going to have only third harmonics, because the rest, they are going to get smaller and smaller. Remember the Q things we had in the denominator, right? We assume here, this one is going to be V3 over V1. This is not the right assumption, but let's assume how good it is, We do this one, and you can go calculate back the THT. Just put it in your circuit simulation to see is it good or not, the assumption we have. So V1 is over V3, so now we can say V3, it should be THD times V1, right? How much is the THD? THD is 5%. Basically, this one, V3, THD should be less than 5%, right? So basically from these two, we say V3 over V1 should be less than 0.05, right? So V3 should be less than 0.05 times 55 and a half. So V3 should be less than 3.54. Right here. If you are worried, I think consider the fifth harmonic, seventh harmonic. Select this one 3. Maybe it's too much. I'm going to get a very good THD. Select 2. You know what I'm saying? You can select it 2 here. Maybe your THD is going to end up 3%. Well, you can go, or you can go with this number and recalculate your THD at the end. You know what I'm saying? To see how bad you are. If your THD ends up 6%, I say, hey, I'm going to go back, repeat this design, go with 3. You know what I'm saying? So this is a kind of try and error for these calculations. Now we know V1 is going to be less than this much. From the equation we got it the other day, VO3, we had a Vn, I believe. We had the equation for, let me see. Yes. We had it VON over V1, we had the equation for that one. If you go to look at your note, we had the VON, we calculate the VON. Let's say VO3 over V1 is going to be, this one, we'll go with this number, 3.54 over, how much was the first one?
55.5.
No, it's this. This one is going to be, I think, 70.7. So it's going to be 70.7. Let me see, let me check this equation quickly. There is a 1 over 3. Let me write this equation. You just remind you guys, this is what we got last class. We got this one. VON is 4 V in over n pi. This is what we have from the last class. 1 over 1 plus q squared n omega over omega 0 minus omega 0 over n omega squared. Right? This is the equation we had from the last class. Let's do this one a little bit, you know. I'm going to bring this one here. I'm going to bring this one here. It's going to be VON. Let's divide it by this one. 4V in over pi. And 1 over n. Is it correct? I divided both sides by this one, right? So basically, this one is going to be VON over V1 divided by n, right? 4V in divided by pi is a V1, right? So basically, my point is here, is VO3, I'm going to go with this equation. Then let's use this one, right? VO3, see, I'm going with this, right? VO3 over V1 divided by 3, right? So I need it divided by 3 here. Times. Yes.
For V1, when we used it to solve for the V3, were we supposed to use the 70.7 there for V1?
Yes, I put it here.
I mean,
Up there.
above that when we did V3 over V1 here.
Yes.
Remember you put down
Here,
this-
you're talking about here.
Yeah.
Yeah. No, I should do that one. 70. Yes, it should be 7. This is times 70 and a half. But it still is going to end up this one.
Okay.
See, 5 times 7 is 3.5, right? Let's see how- That one was wrong. We wanted 2.5 something. Now, this I'm replacing here. VO3, we assume only there is a third harmonic, right? VO3 over V1 over 3, right? This is what I went with the maximum number here, right? I want to have this one. As I said, you can select 3 volts. You can select 2.5. So this one divided by this much is going to be what? 1 over 1 plus q squared, right? 3 omega over omega 0, right? minus omega 0 over 3 omega squared, right? No, I'm sorry, guys. Sorry. This is equal to this. Because this one divided by this is equal, I think where's the equation, right? This one divided by this is equal to this, right? This one divided by this, which is this, is equal to this, right? This is one equation. This one is known, this one is known. Omega 0, how much is going to be? 1000, right? That's the resonant frequency, right? So from this equation, I can go find the Q value. The reason I'm saying 1000 because we want to have 1000 hertz, right? So we want to have a resonant frequency of 1000 hertz, right? So this omega 0 has to be 2 pi times 10,000, right? If you solve this one, it's going to be solving this one for Q is going to result in this number. You are going to get Q equal to 2.47. So I said this omega 0 is how much? 2 pi times. How much the omega is? How much is this omega? This is the resonant frequency, right? How much is the omega? Same, right? Basically, this is the omega 0 also, right? Why? Because we want to switch at the resonant frequency, right? Basically, this one is going to go. Just I want to tell you there is only one unknown. The Q is unknown, right? So you get a 2.47 for Q. So you got a 2.47. Now you can go calculate back LR and you say LR is equal to QR over omega 0. And CR is equal to 1 over Q omega 0 R. So, and how much is the omega 0? Omega 0 is 2000 pi, and R is how much? 10. So you will find out LR is equal to 3.93 millihenry, and CR is equal to
Did the problem tell you to use the resonant frequency?
no. So we designed a resonant converter for that. So we didn't say to use it. We said, remember, we said if you have this circuit, if you are switching at the resonant frequency, these two they are going to cancel each other. We are going to have very nice output voltage, right? This way you can select. You know.
So
One thing is important, guys. You know, if you really want to build this circuit, if you have time, just simulate what I said here. Most probably TXT is going to be a little bit more than 5% because we selected this number, right? We went with the borderline. We assume there is no other harmonics, right? There are other harmonics, but they are small. We went with this number. Most probably it will be a little bit more than 4%, 5%. Basically, come back here, make this one 3 volt, and do it again. You're going to end up less than 5%, right? Now, one thing is very important. You guys go think about it. You know, when you are going to buy these parts, what is important about buying these parts? Capacitor. Basically, capacitor is very clear. Huh?
you want to keep the capacitor small.
ESR is for the DC capacitor, basically. but ESR, less ESR is better. When you buy a capacitor, size, what do you mean size? No, this is the value, we find it out. How much is it? 6.44 multiplied, right? We find the value. So, what else? When if you're going to buy capacitor, what else do you look at? Voltage rating, right? The voltage. But you know, one of the very important things is the voltage rating for capacitor. If you want to design the 12 volt output, you know, voltage, you don't select 6 volt capacitor. Why? getting glued up, right? You go, so if it's a 12 volt, you go maybe 2 times, you know, if you go with 20 volts, 24 volts, something like that. If you have time, just simulate this circuit, and look at this volt. This is one of the another disadvantages of the resonant converter. Look at this voltage here. These two, they are going to be the same, right? Only in different directions because they're canceling each other. The inductor and the capacitor you buy, they should be able to block that voltage. They should be able to handle that voltage, you know. Go look at, see, the maximum voltage here is V is 15.5, but I think if you do this one, the capacitor has to handle up to 160 volts, something like that. So that's another disadvantage of the resonant converters. Resonant converters, they are good, but not very popular, you know, not very popular. They have some good advantages, but they have lots of disadvantages too. This is one simple example. So you will receive the phase 4 of the project tonight for sure. Phase 4. Phase 4 is going to be focused on the MPPT. You guys are going to work on that one. Saturday before the final exam week, we are going to have 11 to 3. We are going to have the presentation. So you need like a 10 minutes presentation, 15 minutes presentation and question. And everybody should participate in the presentation. And we have 4 questions in the final exam. I'll send you the homework number 4 probably Thursday. Then this is where we are, and you will do the last one.
Say homework. Are you ready? Ready as I'll be.